isothermal fixed bed reactor with non-uniformly active catalyst. And our authors are C.K. Lee and A. Borman. Our speaker is Cassian Lee, and this work was done at the University of Notre Dame. Dr. Lee received his B.S. degree at the University of Minnesota and his M.S. and Ph.D. at the University of Notre Dame. Currently is a postdoctoral research associate with Purdue University. Dr. Lee.
Thank you, Professor. Good morning. Can I have my first slide? Okay, the title of my talk today again is an isothermal fixed bed reactor with non-uniformly active catalyst, experiments and theory. The topic of non-uniformly active catalyst has been studied by many researchers since the late 60s. Our research group at Notre Dame started working in this area about 7 or 8 years ago, and we were trying to determine the best way to distribute a fixed amount of active catalyst within a porous particle, such that the catalyst performance is optimized. It's turned out for any kinetics, either isothermal or non-isothermal, with or without external mass transfer resistance, the optimal distribution is given by a derivative function, which means all the catalyst is going to be concentrated as one location within the porous support, deposited as a thin band within the particle. And in this, indeed, we have done some experiments to try to make this kind of catalyst. And this is platinum deposit on gamma alumina. The procedure we use is using the sequential impregnation of carboxylic acid and citric acid. By adjusting the concentration of the two acids and the impregnation time, we can adjust the position of the platinum ring anywhere we want to deposit within the particle. And what we are doing here today is to try to verify the theory that we developed for the optimal distribution catalyst by experiment. And recently we have shown the verification of the theory for a single particle. And today we are going to look at the verification of a fixed bed reactor, which is packed with this kind of catalyst. And I'd like to show you the model that we have for the fixed bed reactor. This is a simple isothermal heterogeneous fixed bed model, which we only use a Plato model, and the kinetics is a Lamian-Schur kinetic. The fluid phase equation, we have the convection versus equals to reaction term in the fluid phase. For the solid phase equation, we actually have the diffusion and reaction taking place in the solid phase. But by substituting into the derivative function as the distribution function for the catalytic activity, we end up with this expression, which actually is the solution to the diffusion reaction equation. And I'd like to bring your attention to several parameters that we are looking at, especially sigma is the dimensionless equilibrium absorption constant we have, which contains K as an equilibrium constant, and also the feed concentration of the reactor. Another parameter is alpha, which actually contains Keeling modulus, Biot number, and also the psi of S bar is the location of the catalyst within the particle, either slab, infinite, cylinder, or spherical particle. And this is the result of our optimization from the model. We actually performed, maximize the conversion of the reactor by adjusting the location of the catalyst within the particle. And the upper bound of the solution is given by the D equals to infinity, which means each particle within reactor has a different location of catalyst which changes along the reactor. Since that is not practical to use, we actually go to a different optimization which only use B=1, which means using one catalyst, the same catalyst along the reactor to optimize the outlet conversion. And also we have done two types of catalysts back in series and also three. Eventually it will finally go to the infinite zone of distribution along the reactor. And we have done some experiment regarding the B=1, the first line here and the second line here, which only have one catalyst or two catalysts within a reactor. And specifically, we have prepared 4 different types of catalysts for the fixed bed reactor. This is just the externally coated catalyst, and with 3 internally coated catalysts, which they have different location of the platinum band. And the characteristics of the catalyst we have is for external is about 51% loading, and the rest of them is about 15 to 20% loading. Seems like the external one has more platinum in it because when we go through the impregnation procedure, we first put the catalyst into the carboxylic acid and let them impregnate for a while, and then take them out. And then the internal catalyst we would put them into a second impregnation step for the citric acid to actually push the platinum band to inside the particle. But we didn't do that for the external catalyst. That's why actually it retains most of the platinum that is being absorbed from the particle, whereas the other one may have actually dissolved from the particle, which retains less platinum into the catalyst. And we have also dispersion data, and seems like they are consistent, except the most inner one we have seems to have a higher dispersion than the rest of them, because I think the most inner one, it had the most longest time for impregnation second step, so it had more time for it to diffuse to give a high dispersion rate. And A is actually the surface area of platinum within the particle over the total volume, solid volume within the reactor. And the thickness of the catalyst band is always less than 5% of the radius of the particle. So this is our schematic of our experimental setup. We are studying CO oxidation on platinum, and we have CO going into the trap to remove some impurity, go through a mass flow controller, and go into the preheating zone in the furnace, and goes through an inert zone and finally catalytic zone. We have thermocouples going in, inlet of reactor and also outlet reactor to monitor the bed temperature. We have oxygen always present in excess to join with CO and go into the reactor. N2 and H2 are the flushing gas and also for pretreatment purposes. And we have 2 analyzers in line. One is CO before the reactor, analyze the feed concentration, and also the CO2 analyze the effluent concentration. And this is a typical result that we obtain. This is for the external catalyst at 115 degrees C under 2 flow rate. As we can see, for the high flow rate result, we actually do see a curve coming down as the feed concentration increases, the conversion decreases. And when we have only a unique solution here at this point, but if we decrease the flow rate, we actually do see a multiplicity which contains a high conversion regime and a low conversion regime. And so if you go slowly from a small CO feed concentration and slowly increase the concentration of the reactor, you would see an extension of a decrease in conversion, a sudden drop and going into the low conversion branch. If you go back the other way, starting at high concentration and go back to low concentration, you would actually see just a continuous change going from the low conversion regime to high conversion regime. And similar results are obtained for the I2 catalyst, which is the band as about halfway within the particle. We have seen the same behavior, which is have one jump going down from high to low, and also a continuous branch going from the low to the high branch. And oscillations are also observed in this region here. As we can see already, by comparing the 2 catalysts, one is internal and one external, we do see some improvement in terms of getting high concentration as the higher feed getting high conversion at some range of CO feed concentration above 1% under the same conditions. And I'd like to bring you back, before we actually use the model to simulate the experimental data, we need to back out some kinetics and also transport parameters. This is our internal, we are trying to determine the intrinsic kinetics for the CO oxidation on platinum. As several investigators have indicated, by Monica Lemon-Hewitt actually does not fit CO oxidation on platinum very well. So we had to go to a surface reaction mechanistic model to actually write all the elementary steps for adsorption and reaction within the catalyst. And then we take the data, we took data using a CSDR reactor and actually fit the data using that model, and it seems to be works very well. Since that model is kind of complicated to use in a fixed bed model, so what we do is just use the nonuniform kinetics into our model and try to get some qualitative behavior to predict what we see experimentally. And this is a result of from our model, which shows the parameter space of alpha. I mean, sigma again is the equilibrium constant which contains the feed concentration. Because in the experiment, most of the time we want to see what happens when we change the feed concentration of CO. And so in the model, we would like to see what will happen when sigma changes. So we want to see what happens if you go from left to right along this figure here. And alpha, it contains the TD modulus and Bayes number and also the catalyst location. So we basically see three regions. One, we have a unique solution. The second region, the inlet of the reactor actually exhibit multiplicity, which can have a high state, low state, or a middle state. And then also on the third region, we have also the reactor would start at one solution, but we would see some kind of a jump along the reactor. But basically, there are only two types of behavior we can have by changing sigma along this diagram, which is for sigma less than 27, we have a unique solution, or above 27, we have a 1-3-1 pattern. And this is a typical diagram you will see by choosing alpha at 220, which is so that picture is along, we get the result along 220 around here. So at the beginning, we are in region 1, which has the unique solution at the high conversion branch. In region 2, we have 3 possible solutions, with the middle branch being an unstable solution and a high and low conversion branch. And on the third region, we have uniqueness again. The main feature of this bifurcation diagram is the unique one jump going from the high solution branch and to the low conversion branch. And we have a continuous curve going from the low and joining to the high. And this is what we see experimentally too. This is some of the other results we have for the I3 catalyst. The one is has the most inner ring catalyst. The same qualitative behavior is seen experimentally, which is as one jump and continuously going to the high conversion branch. And we have got data for 100 degrees C and 150 degrees C at 2 flow rate. And the basic behavior is also seen in both cases. And if we look at the model again and try to see what will happen if we change the temperature within the experiment and see, now we see what will happen in the model when we try to change the temperature. And this is what we see when we increase the temperature, and then we'll get this curve here, B, which is on the right side of A. A has a lower temperature than B. It's roughly 10 to 20 degrees higher. And we would expect the curve would be on the right side when we're high temperature and also have a larger loop. And we go back to this picture again, we are seeing the same thing experimentally, which means at high temperature, let's look at this curve. The loop is around 1% CO, but at 100 degrees C, the multiplicity loop is about 0.6, 0.7 feet%. So the high temperature one would actually on the right side on the low temperature one. And this slide shows a comparison of 4 catalysts that we have tested. And I'm just joining the points showing the highest conversion it can achieve for each set of data. It seems like the I1 catalyst would exhibit the widest range of high conversion regime, and then I2, I3, and then the external one. And so we do see a change in performance by putting catalysts at different locations. And it seems like the I1 in this case performed the best among the catalysts. And also, we have done some experiment by packing the reactor with 2 different catalysts. In this case, we have the first half of the reactor packed with I3, the internal one, and then the second zone is the external catalyst. And we see actually a drastic increase of conversion at this high range of CO3 concentration compared to just single zone reactor, compared to either the external or the I3. So by actually doing a 2-zone reactor, we have a very good improvement in conversion. This is also a dual-zone reactor result, but I would like to show you the order of the packing is important to achieve the improvement that we want, because from the theory, we want to pack the catalyst first with the catalyst which is most inner within the particle, and then the second zone should be more up towards the outside surface. And this is the right order we would want it to be, which exhibit a large hysteresis loop with very high conversion at this end. But if you pack in a reverse order, you would see an actual lower conversion at this end. And at the same time, we have discovered a third solution branch coming down here from this low conversion branch. And that promised to go back to the theory to try to see if we can actually predict that theoretically too. In a model, indeed, we do able to get a third branch, because when a single zone reactor is capable of giving 2 steady state, when I have 2 zones packed in the reactor, theoretically it should get a maximum of 4 steady state. And indeed, at some of the parameter range close to the experimental value, we do see a third branch coming out. And by changing different parameters, the alphas and damper number, we do observe many different possible behavior that you can observe experimentally. Which some of them can have 2 jumps going down, or even an isolated branch, which you cannot obtain by just going up and down. And I would like to conclude the talk by saying that we are able to make a catalyst which has narrow platinum band using the sequential information of propylene acid and citric acid. And we have been using a simple heterogeneous plug flow model to predict what the experimental data would be. Because of the simple model that we have, we are actually getting good qualitative agreement. And because we are using the direct delta function as our activity distribution function, we end up solving the nonlinear differential equation analytically, which is pretty handy to have. And also, good qualitative agreement was obtained between the theory and experiment. 2 stable solution regimes can generally be found in a single zone reactor where only 1 jump occurs, only from the high to the low conversion. And when we have a 2 dual zone reactor, we can expect more than 2 stable steady state to occur. And as the theory predicted, we have high conversion can be achieved by packing the reactor with 2 catalysts, and it can have improvement over the single zone reactor. Thanks for your attention.
Select